All right, howdy folks. Welcome back to the Professor Carbon YouTube channel. In this video, what we're going to do is go over a synthesis problem. And here what we're asked to do is to develop a synthesis starting with dibromo-propane and converting it into this lactone containing a phenyl group. And this will propose some unique challenges, but like all of these Professor Carbon videos, what I encourage you to do is to take a few minutes, pause this video, and really try to address this problem all on your own before just listening to the answers I'll provide. So please do that right now. All right, welcome back. What I'm going to do is simply just talk through some of our retrosynthetic disconnections and then maybe some problems with putting these steps in the forward direction. And then there will actually be quite a few different possible correct answers here. So starting with this, let's just think through a couple of key observations. So one of which is if I number these, 1, 2, 3, 4, we're going to obviously have to come up with a way to add that phenyl group in there, but we're only given 3 carbons in our dibromo-propane. And so that means at some point we're going to have to figure out a way to add 1 carbon. And there are a few places that we like to go to when trying to add 1 carbon. And so immediately what I like to think about is either cyanide or carbon dioxide. And so both of these have the potential to add exactly 1 carbon to our molecule. Now, the ester here, we can imagine breaking on that bond, and that would take us back to, an acyclic carboxylic acid and alcohol, and that would probably let us recognize some other ways to make this. So for now, for those of you that wanted to use your CO2, you might be tempted to imagine adding in, a bromide via Grignard reagent, and then have that CO2 over here. And I'll talk about that there are some key pitfalls here, because this is probably one of the #1 most common problems students have when I put this on an exam, is that they want to make this Grignard reagent or one like it, but there's a big problem. And this is a highly basic Grignard reagent, and we have a highly acidic OH group there. And so it is incompatible to have any OH group with any Grignard reagent. There just deprotonates itself, and then you have, the wrong reaction. And so we can't do this with that oxygen there. Now, we could, in principle, try some other protecting group sequence. And so some of you might be familiar with the OTBS protecting group. That would be an option. Some of us might be familiar with the O-benzyl protecting group. But remember, this too is a benzylic oxygen bond. And so we would hate to try to remove a benzyl group and accidentally remove the wrong one. So that's a consideration there. And in general, if I have my choice of working with sodium cyanide or trying to get a Grignard reagent to attack carbon dioxide, I personally would rather use sodium cyanide because that chemistry is all compatible with water, and it doesn't require a lot of super special conditions in the lab to very carefully dry all of our apparatuses. So that would be my personal preference. So, another thing to do then might be to consider exactly that. What happened if we have a nitrile here? So that is quite a good way to go about it. And then we could imagine taking this back and breaking this bond, and then we would have an aldehyde. And then we can imagine taking this back to our starting material. And so it turns out that this is going to be the pathway that I put down when I put this on the exam. And so my key was as follows. So I took sodium hydroxide to do an SN2 reaction. And we have 2 equivalent bromines here. And so it doesn't really matter what kind of chemistry we're going to do. These are both primary alkyl bromides. We're going to end up having to eat a low yield at one of these steps. And so even if we have exactly one equivalent of sodium hydroxide, we're going to end up with some of this product that has undergone double substitution. We're going to end up some of what would be the desired product. And then we'll end up with some unreacted starting material. And realistically, to get this reaction to go, we would have to use excess hydroxide anyway, because typically aqueous hydroxide is not the world's greatest nucleophile. All right, but there should be some way to get that substitution reaction to occur. Then we could imagine doing sodium cyanide to displace the other half. And that'll bring in our very important fourth carbon. Now, for those of you that are curious, realistically, you could probably do these steps in the reverse order, where we put the nitrile in and you put the hydroxide in second. The little bit of a hiccup, though, is remember, you can partially hydrolyze nitriles under strongly basic conditions. And so we would avoid a potential functional group incompatibility issue by using the sodium hydroxide first and then incorporating the nitrile second. Now we can oxidize the alcohol up to the aldehyde. And I want to point out something here that's a little bit more subtle. So this is an alpha and we have a beta carbon there. And nitrile is not the best leaving group, but we could imagine reversing these steps and generating the bromide here and then trying to carry that forward. That would be a problem. So any leaving groups at these beta positions, if you have an equilibrium to the enol, which we know is always a competing process, these beta leaving groups can get kicked off, especially if they're really good leaving groups like bromine. And so this would probably tend to eliminate off and make the molecule acrolein plus HBr. Now, that would happen best with a little bit of base around to maybe make a little bit of enolate instead of going through the enol, but it is possible under either set of conditions we could draw that. And so carbonyls with leaving groups in their beta position are highly problematic synthetic intermediates. And so here it's probably highly advantageous to have the nitrile, which is a much worse leaving group than bromide, be incorporated before we go up to the aldehyde oxidation state. In either case, from here we have, now we can use our phenyl magnesium chloride. And of course, both nitriles and aldehydes can, in principle, be attacked by a Grignard reagent. But the advantage we have here is that aldehydes are a lot more reactive than nitriles, often, maybe 1,000-fold more reactive. And so we should have very good chemoselectivity for the aldehyde being attacked instead of the nitrile. So that would get us to here. And now what we can do is a couple step hydrolysis. So I can take this with H3O+, and that way we could hydrolyze the nitrile to the acid. And then we could imagine some more H+ or H3O+ to cyclize that alcohol onto the acid carbon and make the lactone. Now, in principle, and perhaps more realistically, we could try to do this all at once. And since acid is doing both steps, of course, we might be able to find the right acid and the right sets of conditions that hydrolyze the alcohol or the nitrile and then close it all the way down all at the same time. And so, yes, of course, we could imagine doing that. So this is probably what I would consider the most straightforward set of synthetic steps to get us there. But I'm always proud of students that come up with really exciting answers that perhaps I didn't consider. And so let me walk through a couple of those that I was excited about. Oh, and I'll remind you the number one biggest hiccup here is students combining Grignard reagents with OHs. And so anytime you have either on a carboxylic acid or as an alcohol, you can't have a Grignard reagent because that strongly basic Grignard reagent will simply deprotonate that OH, and then you'll make O- and your Grignard reagent will be shot. Okay, a couple of really nice sequences some other students thought about. One of them was to take this dibromide and treat it with sodium cyanide first. And so that made the bromonitrile. And then very cleverly, they thought 1, 2, 3, 4. Well, what happens if I treat this with magnesium 0? That should make my magnesium nitrile. And now I have that strong nucleophile right around my strong electrophile. And so after I hydrolyze it with some acid, what it should end up here with is actually a 4-membered ketone. And that's pretty clever, I thought, for students to recognize that, especially when we see how they'll complete the molecule. So from here then, what the students wanted to do was to use phenyl bromide to get to this product where we have a phenyl group. Oops. And of course, we can do ketone alkylations from the enolates, so that's relatively standard. And we like then if we have especially primary leaving groups, we can do this SN2 reaction to do that alkylation. But of course, this is SN2, and on bromobenzene, we can't do backside attack, right? It's an sp2 hybridized carbon. And so that antibonding orbital would be somewhere in this ring for that C bond. And so we can't do that, but it turns out you can do what's called ketone alpha arylation if we throw in a little bit of palladium. And so that helps us engage a different mechanism, and it'll actually let you overcome this as long as you also have some strong base. So maybe we'll put in some potassium terpbutoxide to represent the strong base. So even if the exact details weren't right, I liked the logic. And I'll point out that even though this reaction is not covered in most textbooks, it is known in the primary chemical literature that you can do these ketone alpha arylation reactions. What I thought was the most clever about this sequence, though, was that the student recognized that now they have two sides on this ketone, and that this side now is tertiary and this side is secondary. And what that means is they could do the Baeyer-Villiger oxidation to put the oxygen on the correct side. And so I thought that that was really awesome. So good work there. I thought that that was quite a clever solution. Definitely not something I would have thought of. The second answer that I thought was also quite clever is that students engaged some chemistry from a prior chapter and remembered that you can take these cuprates and do an SN2 reaction on primary or secondary leaving groups. Remember, you need the cuprate because if you have a Grignard reagent or a organolithium reagent, so if I have bromine here and I have an H here, our lithium reagent is strongly basic, and it'll instead do that pesky E2 reaction. And so remember, any time that you have a strong nucleophile, odds are good it's also a strong base. And unfortunately, E2 reactions can compete with our SN2 reactivity. And so the cuprate ends up being the choice reagent here to facilitate the SN2 instead of the E2 reaction. In any event, that lets us get to this reagent. And then we can take this with our cyanide and do the same SN2 reaction. And now it would seem that you're stuck, but this student remembered that we have really nice benzylic bonds here, and they actually used a benzylic bromination, Br2 and HV, UV light to irradiate, and that lets them do the benzylic bromination, which should be selective for that benzylic spot because we have a weaker bond association energy for the H atom abstraction that's key to that radical mechanism. So I thought that was clever. Then they were able to hydrolyze this, so H3O plus to the corresponding acid. And then use an SN1 reaction, which should be facilitated by having the phenyl group here and give off HBr, and then that would make the lactone a very slightly different way. And so again, I thought that that was a very clever approach to solving this problem, and I didn't see any fundamental flaws in the chemistry, so I liked this answer as well. So as with all of these synthesis problems, there's typically more than one correct answer. And that's part of what makes organic synthesis so much fun, is then trying to go in the lab and figure out which of them is actually the most efficient pathway. So hopefully you enjoyed this video. Please do subscribe to us on the Professor Carbon YouTube channel. We really do appreciate those subscribers. Also feel free to tell a friend about us, share us on social media, give us a like, leave a comment in the video. And again, if you want access to these PDFs, you can follow us on Patreon. Thank you.